The next presentation is about the creation of new biomaterials. It's going to be presented by Henrietta, who studies at Precivitas Malmö and has competed in both biology, chemistry, and volleyball. Welcome, Henrietta.
Please raise your hand if you ever used a diaper when you were a kid. Well, every single one here have used a diaper. And we probably look something like this baby right here. Happy, blissful, trusting the absorption capacity of the diapers. But we didn't know the environmental effects that diapers have upon the environment. And we also use a lot of plastics in these diapers. But plastics are also used in menstrual pads and many different products within the sanitary sector. Unfortunately, these plastics are crucial for the plastic pollution that we see in the environment right now. It takes roughly 22 kilograms of fossil fuels to produce the amount of diapers that one baby uses throughout 1 year. And a person that menstruates accumulates around 200 kilograms of menstrual pads. Unfortunately, the plastics used in these materials degrade, but it does take around 500 years to do that, and it doesn't even degrade fully. Microplastics remain, which are released into the environment and impact the environment crucially and a lot. We need to find a better solution, something to replace the plastics currently used so that it is more sustainable. Because right now, the absorbents in menstrual pads and in diapers are made from lightweight synthetic polymers, specifically rayon and polyester. And what's really special about these are that it's plastic, thus contributing to plastic pollution. As seen in this image right here, an SEM image, meaning scanning electron microscopy, we can see that the first layer here have rather large pores, and that is for the absorption to be facilitated. The second layer have smaller pores, which aims to prevent leakage. But, as I said, plastic is a huge problem for us right now. We're facing an environmental crisis. So, what I was trying to do is to create a material by using biopolymers to create lightweight absorbents that can be used in menstrual pads and in diapers because they are biodegradable. And I specifically used polysaccharides and proteins. So what I first did was to create the solutions using two different polysaccharides, polysaccharide 1 and polysaccharide 2. And I mixed the polysaccharides with the protein in different ratios, and I added water, which can be seen in this image right here. Then I put the solutions into a form, and I heated it up, and they formed a gel. It went through gelification. Secondly, I froze the solutions and the water formed ice crystals. Later, the formulations were put into this lyophilization machine, which is a fancy word for saying a freeze-drying machine. And what happened there is rather interesting because the ice crystals sublimated into gas, leaving behind empty space. And this empty space is crucial for the absorbency of my materials, because empty space is is the pores within the materials. And the materials look something like this. These two images were produced using a data light microscope, and the material looks rather porous, don't you think? And it looks lightweight. We had to use some analysis for this. So we did some absorption tests. We also analyzed the density as well as the chemical and the structural properties of the materials produced. First and foremost, the absorption capacity was evaluated using 3 different methods, whereas one of these was visual absorption capacity, also known as VAT. And the VAT was performed using defibrinated sheep blood to mimic menstrual fluids, and saline, a sodium chloride solution mimicking urine. So we forget about the blood right now, we took a dry sample and we weighted the amount of liquid that was absorbed and divided that with the dry weight of the sample. And that gave us this really beautiful bar chart. We can see the VAT of the samples. And what's really interesting is that all samples show better capacity for absorption of sheep blood compared to that of saline. Furthermore, 3 samples, these 3 right here, indicate better absorption compared to the actual menstrual pad. Well, what is this beautiful picture? A beautiful pink flower, you may think. It's true, but we also have something on top of the pistil of the flower, and that is one of the materials that I produced. As can be seen in the picture, the pistil of the flower is unaffected by the material being on top of it. It doesn't bend, it's not affected, meaning that the density of the materials that I produce are likely quite low, which is also illustrated in this bar chart right here. And something that is really interesting is that all the materials that I produced using biopolymers show a lower density compared to the density of the plastic sanitary pad. And these are really promising results, considering that it would be quite tough for a plastic diaper or a plastic sanitary pad to weigh around 2 kilograms, when the baby itself might only weigh 2 kilograms. Not really sustainable. Thus, these results are very, very promising. But we also evaluated the chemical structures and properties of the materials using SEM. And here we see two different samples, both containing a polysaccharide, namely saccharide 2 and saccharide 1. And the structures are rather different from each other. Here we have the more classical pores, you know, the sponge used in the kitchen. Think of it like that. Meanwhile, the pores right here have formed more like a filament type layer. And this is most likely due to different polysaccharides used, but also due to the ratio between the polysaccharide and the proteins. Moving forward, we analyzed the chemical properties of the materials using the FTER spectrum. And what's rather interesting about FTER is that chemical bonds showcase specific peaks. And those peaks are illustrated here. And we can see a specific peak, two peaks called amide 1 and amide 2. And these peaks are really significant for proteins. Moving on, we also see a characteristic glycosidic bond in this peak right here, showcasing that there are polysaccharides within the material as well. And then lastly, we have this peak, or these peaks right here, showcasing normal bonds within both polysaccharides and proteins. Hence, we can come to the conclusion that the materials probably both contain polysaccharides and proteins. But what's even more interesting are that no further peaks are shown in the spectrum. Thus, no new bonds between the polysaccharides and the proteins have formed. So the conclusion is that all the materials produced using biopolymers showcases lower densities compared to the density of the actual plastic sanitary pad. Furthermore, all materials showcases better absorption for defibrinated sheep blood compared to the absorption of saline. Thus, these materials might be better potentially suited as an alternative to the lightweight plastic absorbents currently used in menstrual pads. Considering this, future studies could aim at trying to evaluate how non-defibrinated sheep blood affects the absorption as well as the porosity of the materials to better and find a solution that better mimics menstrual fluids. It might also be advisable to try to mimic the structure right here, trying to manipulate the sizes of the pores to create larger sizes that will facilitate absorption, but also smaller pores that will prevent leakage. So even though the materials that I produced showcase the better absorption for sheep blood, we should not forget the aim of the study, to try to replace the plastics currently used in both diapers and menstrual pads. Because future generations should be able to use diapers that do not affect the environment as much as they are right now. I want to thank my excellent mentor, Antonio Campesa, as well as Mercedes and Anthony for all the assistance in the lab. I thirdly want to thank Race for Excellence and its sponsors, Stiftelsen Bengt Minne and Binger Stiftelsen. And obviously I want to thank all the X-rays for providing assistance with the writing process. Thank you for listening.
Thank you so much, Henrietta. Are there any questions in the audience? Yeah?
I would like to thank you about the presentation and the purpose of the study. So actually I have a few questions and maybe a recommendation. So the first one, how do you think about the of raw material, with like, if it's a big commercial product, where
with the polysaccharides and proteins. And we use byproducts from the agriculture, meaning that the products that we use are like rest products. So instead of throwing that away, we can use that to produce the lightweight absorbent products, and thereby kind of closing the circle and preventing using new materials.
Sounds great. The second one.
Mm-hmm.
After, like, when it's absorbed, if it's the natural as or neuron, so do you think about it will be a good media for microbial growth? Do you know if there is a study about that? So how the frequencies to change, because it will be a good media for microbial growth.
I think previous studies have shown that some of the materials are antimicrobial and they're non-toxic, but I think it would be advisable to do further research, and when if we're going to use these products in actual menstrual pads, we have to conduct more research and testing the safety of the products and make sure that, as you said, no bacterials are produced. Yeah.
Thank you.
No worries. Yeah?
Why is the absorption actually better than the research?
Well, it might be because of the amount of particles within the solutions, because the absorption is due to osmolarity, and when you have more particles, that changes how much we'll absorb. And saline, containing both sodium and chloride, changes the amount that is absorbed. Yeah?
Do the raw material or the polysaccharides and protein absorb the humidity from environment?
The what?
Absorb humidity from environment?
That is a good question. I have not tested that, so maybe that is another thing that future studies could test. But I mean, if you can absorb saline, it can probably absorb water and things from the air as well.
Okay, seems like there's no more questions. Thank you so much, Henrietta.